Morning. I am Dr. Ramesh Kumar, Assistant Professor of Chemistry, PSM College of Engineering and Technology, Tirunelveli. So this is my second lecture on nanomaterials characterization. So in my previous lecture, I have explained about scanning electron microscopy. So today I will mainly focus on transmission electron microscopy under nanomaterials characterization. So both scanning electron and transmission electron microscopic techniques coming under the electron probe characterization methods. These two techniques mainly involves the electron beam. So based on the secondary effects produced after the interaction with the sample, the different scanning or transmission electron microscopic techniques will be adopted. So both are electron probe characterization methods. So the two techniques will play with the electron beam. So electron probe characterization methods in particular are mainly important to nanoscience due to their capability to analyze structure of extremely small particles. Nanometer sized particles will be analyzed through scanning electron microscopy and transmission electron microscopy. Of course, transmission electron microscopy is far better in the sense we can analyze extremely small particles when compared to the scanning electron microscopy. So in the last lecture we have seen the scanning electron microscopy, which involves the secondary effects, scattered electron and backscattered electron and the secondary electron, which are the responsible for the image production. In this case, in transmission electron microscopy, we will be studying about the transmitted electrons and inelastically scattered electrons. They are also having their own advantages. So we will see one by one. So both techniques, the electron probe methods, use high energy electron beams. The electron beam energy or the acceleration voltage may be different for scanning electron microscope and transmission electron microscope. Transmission electron microscope, of course, use the high acceleration voltage. For example, in the range of 200 to 500 kilovolt, the energy will be used in the transmission electron microscope, whereas in scanning electron microscopy, around 50 kilovolt acceleration voltage was used. So that details we have seen already. So anyway, once again we will see the central aspects of the electron probe methods. So both the techniques, both the microscope will use high energy electron beams, and the electron beams are used for imaging, chemical analysis and the determination of material structure. So in this sum, the electron beam is rastered across the analytical surface. A raster is a rectangular pattern of a parallel scanned lines from which image can be assembled. And both technique, both the SEM and TEM instruments, they are usually coupled with other analytical tools. They are other accessories like EDS and SAED. These techniques will be useful for obtaining the crystal structures or the element present in the sample. So we can analyze it by adapting by coupling TEM or SEM instrument with the EDX or SAED accessories, electron diffraction analysis, energy dispersive X-ray, and selected area electron diffraction. So main techniques are SEM and TEM. These instruments may be coupled with other accessories to get the allied data like the crystal structure and the fringe patterns. So these kind of things we can analyze. So commonly these two techniques are used for obtaining morphology of the material, the size and the shape of the material, topography of the material, and the crystal structure of the material, and the atomic arrangement at the surface of the material. So these information we can get it from the SEM and TEM analysis. So fundamentally, when electron interacting with the matter, so there will be the production of the interaction volume. So the electron beam will be scattered. So the scattering will be depending on both scattering cross section and the mean free path of the electron. And after interacting with the sample, there will be a production of interaction volume. So this interaction volume will be around 105 micrometer size. So the interaction volume is directly proportional to the beam voltage. When we apply high beam voltage, the volume will be higher. And if the thickness of the film is small, then the volume will be higher. So the interaction volume will be higher. So the interaction volume, the electron beam interaction volume, that is otherwise called the volume of excitation, is directly proportional to beam voltage and indirectly proportional to specimen density. So usually thick samples are analyzed through scanning electron microscopy, and for thin samples we can adopt transmission electron microscopy. So as I said earlier, backscattered electrons and secondary electrons are the major components for the scanning electron microscopy. So they are the responsible factors for creating image on the screen. But in the transmission electron microscopic method or analysis, so the main electron is transmitted electron. The electron beam produces high energy electron, fast moving electron. After interacting with the sample, some of the electrons will be transmitted without getting disturbed. So these are the main sources for the production of images in the transmission electron microscopy. And other two important electrons are inelastically scattered electron and elastically scattered electron. So we will see one by one. So what are their key role in obtaining the information about the sample. The important secondary effects exploited in them is secondary electrons, transmitted electron, so which is mainly for production of imaging, and other important electrons are elastically scattered. These electrons will be used for the simultaneous structural analysis by electron diffraction. So by electron diffraction we can get to know the crystallinity of the sample and characteristic X-rays for simultaneous detection of the elements present in the sample, that is EDX. And inelastically scattered electrons also will be detected for analyzing the lattice fringes of the sample. Through the lattice fringes we can analyze the interatomic spacing present at the sample surface. So usually thin samples are analyzed by the transmission electron microscope. So transmitted unscattered electron. So there will be no interaction between electron and the sample, and the electron just transmit through the sample. So acceleration voltage in the order of 100 kilo electron volt. Transmission capability is inversely proportional to thickness. So low atomic weight material transmit electron and appear to be light in the phosphor image screen, and the heavy elements are the elements with higher atomic number interact more strongly than the lighter elements, and they will appear as the dark regions in the image screen, phosphor image screen. So this is a very important aspect of the transmission electron microscopy. So if we have two different elements in our sample, we can analyze through the photograph. So image with light color or image with the image appears as light will be the will be having low atomic number, and the dark image indicates the presence of heavier element or the element with higher atomic number. And particle size can be easily measured through transmission electron microscopy. So it is always good to compare the size obtained from the transmission electron microscopy with the size obtained from the other techniques. So in addition to that, gives you the direct idea of the crystallinity of the sample. And the elastically scattered electrons, the electrons will be deflected after interacting with the sample, but there will be no loss in energy. So this process will be governed by the Bragg's law of diffraction. So the elastically scattered electron adhere to Bragg's law of diffraction. So elastically scattered electron are mainly used for generating electron diffraction pattern. So as I said earlier, the selected area electron diffraction. So the beam, the electron beam will be focused on particular area of the sample surface. So that will create a ring patterns. It will show what kind of crystalline phases present in the sample. So information concerning crystal structure and orientation about the sample is acquired from the patterns. Typically the H scale values. So what is a typical phase, crystal phases present in the sample, we can acquire from the elastically scattered electron. So otherwise we can say these kind of information, the crystalline property of the sample obtained through the passage of elastically scattered electron. And inelastically scattered electron, they will lose energy after hitting the sample surface. They are also transmitting through the sample, and so these are the main electrons which will produce Kakuchi bands related to the atomic spacing. The Kakuchi lines we can easily observe from the dummy image, so which are produced by the inelastically scattered electron. So that will give you the interspacing value between two atomic lines. So the inelastically scattered electron that participate in the formation of Kakuchi lines or Kakuchi bands, so that are related to atomic spacing of the specimen. the width of the Kakuchi line is inversely proportional to the interatomic spacing. So this is the main information we can get it from the inelastically scattered electron. So from these two slides, so we can easily understand the transmitted electrons are responsible for image production, and the lighter and dark images will give you the idea about the heavier and the lighter elements. So element with the low atomic number will be showing us the light image, and the elements with higher atomic number will be shown as the dark image. Then elastically scattered electron will give you the information about the crystalline nature of the sample. Inelastically scattered electron will provide the will produce the Kakuchi lines, Kakuchi bands. So from that we can get the idea about the interspacing value, the space, the distance between two atomic layers. We can measure it from the image. So what are the different key aspects or components of the TEM, transmission microscopy? So TEM functions by the principles as sum except the detector. So same principle is followed in the transmission electron microscopy, but only the different is the detector system. That is here we are using the passport plate to capture images formed by the transmitted electron, and of course the acceleration voltage in terms of 300 kilovolt. Typically in scanning electron microscopy we use 50 kilovolt. Some instruments will have less than 50 kilovolt also, and wavelength of the electron beam in TEM in the range of 6.13 to 2.24 picometer. And here the electron source is thermionic electron gun, which consists of filament containing tungsten or lithium hexaborate. The material present in the film may be varied depending upon the instrument manufacturer. So typically the instrument uses tungsten or lithium hexaborate. So usually in a typical process, filament is heated under the applied potential until the electron are produced, and the produced electron will be accelerated through the apertures in the range of 300 to 500 kilovolt. So depending on the instrument configuration. So some instrument will be mere term transmission electron microscope. Some instrument may be HR term, high resolution transmission electron microscope. So the main difference is that the difference in the acceleration voltage. In HR term, the instrument will have a higher acceleration voltage, for example 500 kilovolt. So in the term, the important lens system, that is projector lens system, are present at the base of the column, and finally the image will be produced on phosphor screen. So that is the projected image of the sample. So in a typical schematic representation, so we have the electron gun at the top. The electron gun will produce the electrons, high energy electrons, that will be accelerated through the aperture, and there will be a condenser lenses to focus the electron beam to focus towards the sample, and after passing through the sample, again the electron beam will be focused through objective lens, and there will be another aperture, and finally projector lenses are available. So they will focus the transmitted, the inelastically scattered or elastically scattered electrons towards the sample, towards the camera. That is a detector system. charge coupled device. So that will create the image of the sample. So there will be a conversion of the photon into the image of the sample. So how it is happening, we will see in the next slide. So TEMs are capable of significantly higher accelerating voltage. So their resolving power in the range of 0.05 nanometer. So in the scanning electron microscopy, we could only get the image up to 100 nanometer scale bar range. But using transmission electron microscopy, we can go up to 0.05 nanometer. So TEMs are usually equipped with in situ EDX to study the electron diffraction and the different elements present in the sample. And TEM always considered as the crown jewel of nano tools. So very important tool to analyze the nano-sized materials or nano-structured materials. So these are the typical components present in the transmission electron microscope. Electron gun, different kind of lenses. So each lens have their own purpose, and a phosphor screen and a detector system and the monitor to process the images. So thermionic or field emission gun accelerate the electrons between 100 to 400 kilovolt. Some HRTM high resolution instruments may have 500 kilovolt acceleration voltage. So this acceleration will be done by the anode plate and collimated via an aperture, as we have seen in the previous slide. So electron passes through the double condenser lens system to focus the electron beam upon a sample. So specimens 1000 atoms or less in thickness, few nanometer to more than 100 nanometer. The sample specimen will be in the range of 1 micrometer thickness. So in that specimen, the sample will be coated as a thin film. The thin film thickness will be in some nanometers. So the electron that pass through the sample are focused by the objective lenses. So again it will be channeled through the aperture and projected onto the phosphor fluorescent screen by the projector lens. So we have the condenser lens to focus the electron beam, and again we have the objective lens after passing through the sample. Then we have the projector lens. Projector lens direct the electron transmitted electron beam to the image capturing system. That is called a photographic Polaroid camera, or by a charge coupled device, CCD camera. So the image will be processed. So after impinging on the photographic plate, there will be emission of photons. That photons will be converted into image. So actually the transmitted electron will be converted into image. So one more process in between the transmitted electron and the detector will be happening, that is the conversion of electron into photon. So once it strikes the phosphor plate, once the electron strikes the phosphor plate, there will be emission of photons. That photons will be converted into the observable image. So each component has its own role. So thermionic or field emission gun produces the high energy electron that will be accelerated between 100 and 400 kilovolt. The accelerated electron will be condensed through condenser lenses, will be focused towards the sample. So after passing through the sample, there will be some kind of lenses that is called objective lens, and objective lens again channel the electron beam towards through the particular aperture and focus it on the the passport screen with the aid of the objective projector lens. That will project the beam on the electron beam on the passport screen. So in that screen, the electron beam will be converted into photons. So photons will be converted into image by using charge coupled device or photographic Polaroid camera. The CCD camera or photographic paper captures the shadow image of the specimen depending on this density of its components present in the sample. So CCD cameras are comprised of closed packed photodiodes. So in the CCD camera we have photodiodes. So they convert the photons into image. When a specimen image is ready to be recorded, the viewing passport screen will be adjusted so that the camera will be opened, and upon completion of image acquisition, the viewing screen is replaced to its original position. So once the image is ready to be taken, then the passport screen is slightly adjusted so that the camera will be opened. So it will capture the image and we will see the image on the computer screen. And the resolution of good term efficient term will be 0.2 nanometer. So this is on par with the distance between two atomic layers. So that kind of resolution, that much resolution we can get it from the transmission electron microscopy. The atomic level arrangements can be seen can be easily identified through the transmission electron microscopic images. In the year 2005, Carl Zeiss announced a major breakthrough that their TEM resolution was 0.07 nanometer. So with an experimental ultra high resolution 200 kilovolt field emission can transmission electron microscope. So using this transmission electron microscopy, they achieved 0.07 nanometer resolution images. So this level of resolution is near the theoretical limit of transmission electron TEM analysis. So from this information we can come to know that, so from the TEM image we can clearly see the presence of atoms in the sample. So atomic level resolutions can be easily identified through the transmission electron microscopic images. So how image is generated through the transmission electron microscopy? So as I said earlier, transmitted electrons are responsible for generating bright field image of specimen. When the objective aperture is positioned just below the specimen, only transmitted electron beam will be allowed to pass through the column. So we can calibrate or we can adjust the column in such a way that the transmitted electrons only be passing through the column. So that will produce only particular type of sample, that is bright field image of the specimen. So any diffracted or inelastically scattered, the electrons are excluded from passage. So we can avoid diffracted or elastically scattered electrons by doing some adjustment in the objective aperture. So if we exactly say, that is the aperture will be positioned just below the specimen, so that only the transmitted electron beam will be allowed to pass through the column. So if you want to acquire a low resolution dark field image, the aperture may be readjusted or repositioned, while the metal plate will be inserted to block the major beam, that is the transmitted beam. So if we block the transmitted beam, we can obtain low resolution dark field image with the aid of the elastically and inelastically scattered electrons. So although spherical aberrations are found in this configuration, a quick identification of specimens that produce diffraction patterns is accomplished. So diffraction patterns usually get it from will be getting from the elastically scattered electrons. Okay, so main beam, that is transmitted electron, will produce the image of the sample, and if we block the main beam, using the elastically scattered electron, we can get it from we can get the crystalline information about the crystallinity of the sample. So further we need to adjust or tilt the objective aperture. We have to do the repositioning of the objective aperture so that we can get the extra information, that is crystallinity of the sample. And we can get the high resolution dark field image from the transmission electron microscopy analysis. So in this configuration, electron diffraction patterns can be obtained. Electron diffraction pattern can be obtained. So on the other hand, we can allow all the beams which are coming from the electron gun. So all by allowing all beams, that includes transmitted electron elastically scattered and inelastically scattered and the direct electron beam. So these will form another type of images, and so which will show you the lattice fringes of the sample, which will show the Kakuji bands, and which will give you the idea about the interspacing between the two atomic layers. So these are called high resolution lattice images or lattice fringes. We usually call it as fringe patterns of the sample, lattice fringes. We can measure the distance between the two atomic layers. So every image we can see the scale bar at the bottom of the image. So based on the reference scale, we can measure the interatomic distance of the sample. So with HRTEM, it is possible to obtain the combination of bright field and lattice imaging. Real and reciprocal space can be observed simultaneously. So in HRTEM instrument, using the HRTEM instrument, we can obtain both bright field and lattice imaging. Lattice imaging or lattice fringing is the high resolution image. So when we go for 2 nanometer or 1 nanometer scale bar magnification, we can get the atomic level resolution, so that we can identify or we can measure the interatomic spacing. So using the interatomic spacing, we can convert the interatomic spacing into the crystalline facets. So through which what kind of material present in the sample and what kind of facets available at the surface of the sample can be easily monitored. So through the D spacing value or D value, we can identify the crystalline facets, and through the facets what kind of material present in the sample we can easily identify. This is a transmission electron microscopy operation. So samples usually having the thickness less than 100 nanometer, the specimen should be very thin, and the specimen is usually placed on a copper grid with the 3 millimeter dia. The specimen, the copper grid thickness may be 100 micrometer. So copper grid thickness will be 100 micrometer. On that copper grid, the samples will be coated. That will form a thin layer of the sample. That layer thickness will be less than 100 nanometer. The specimen is prepared several ways depending on the sample. The mechanical polishing may be adopted to make a thin film of the sample. So in that mechanical polishing, the sample will undergo ion milling process. Following ion milling, the argon ions will be bombarded at the sample in order to get the thin film of the sample. And other type of sample for colloidal sample, we can sonicate the sample for the good dispersion in that medium, and the sample will be liquid sample will be coated on the copper grid, and it will be air dried. After drying the sample, we can go for the TEM analysis. So it will make a thin film. After drying, it will make a thin film on the copper grid. And sometimes the biological samples also can be analyzed. So depending on the nature of the sample, the color also will be different. For example, for the thin film of the sample, so we can observe the light color, and for the thick sample, biology will be analyzing biological samples. If it is a thick sample, the color will be dark. So we can understand how the nanomaterial property changes once converted from bulk to nanometer size. From the color difference itself, we can come to know the properties have been changed when it is converted from bulk material to nano sized material. So the heavy atom sites appear darker because of better scattering and absorption of electrons. The heavy atom sites, the elements having atomic number, they will experience better scattering and absorption of electrons when compared to the lighter elements. So this will be the key information when we mix. For example, if we have the alloy particle having two different metals, so we can easily identify from the image which one is the less atomic material, and which one is the element having higher atomic number. We can easily identify through the depth image. So the element with the higher atomic number will scatter the electron more, or the absorption of electrons, the amount of absorption of electrons will be more. So that will show a dark image in the screen. So depending on the sample, we can go for the different techniques for the grid specimen preparation. So we can mechanically do the film formation to get a thin film of the sample with less than 100 nanometer. And if it is a colloidal solution, we can trap cast the solution on a grid. We can dry it, it will form a thin film of the sample. Then we can place the specimen in the sample folder, we can analyze it. So even though TEM has a lot of advantages, it has some limitations. So it may not be applied for all types of samples. For example, for organic samples or some biological sample, so they cannot withhold the high energy electron beam. So once we pass the electron beam, the structure of the material will be disturbed, the organic materials. Then we will focus while doing analysis, we will focus only the particular area of the sample. So that will give you some idea about the sample. For example, size and shape of the sample and crystalline property and the element present in the sample. So this kind of information we will be getting by analyzing the particular area of the sample, and we cannot predict the property of the whole sample using that information. So we have focus using that camera, we are focusing the particular area. So that information may not be applicable for the other portion of the sample. So this is the main drawback, and it is a high vacuum instrument. It is very costly to operate and to maintain. Extensive sample preparation is time consuming. Sample preparation is time consuming and the expensive sample preparation. The instrument itself, high cost instrument, and it may not be applicable for the all the samples. That electron beam will disturb or destroy the sample. We cannot get the correct information, and it will analyze the particular part of the sample. That information may not be same to the other part of the sample. So we cannot predict, we cannot exactly say the whole sample having these kind of properties, we cannot say. So in the particular area, the sample having these kind of particles, these kind of crystal structures, and these are the elements present in the sample we can identify. But so anyway, the advantages of TEM technique are numerous, as we have seen just now. So we can analyze it, we can analyze, we can get the lot of parameters from the sample, nanometer, nano-sized samples. So this is the photograph of GeolGem 3200FS field emission transmission electron microscopy. This term is equipped with a 300 kilovolt FEG field emission gun. It is able to conduct EDX, energy dispersive X-ray, energy loss spectrum, and the energy diffraction analysis. So in this particular instrument, the electron gun is zirconium oxide and tungsten. So that is depending on the manufacturer. They will use a different kind of electron gun. Only the electron, the condition is electron gun should produce the high energy electrons. So this instrument is capable of detecting 0.17 nanometer particle size range. So these are some of the TEM images which I have covered for my samples. So these two images are silver nanoparticles. So we can identify through this scale bar. The size of the nanoparticle can be identified this scale bar. We can measure this scale bar, and we can just apply for the single particle. We can identify. We can measure the particle size. So this is a partly dispersed sample. The sample having different sizes, particle with different sizes, and some information I have got. Some twained structures are twained surface is available on the particles, and the particles are spherical in shape. These are not high resolution TEM images. If it is a high resolution TEM image, we can see the arrangement of atoms with the 1 nanometer or 2 nanometer scale. So if we focus more, if the instrument is capable of focusing zoom in more, then we can get the idea about the lattice fringes of the sample. So this is the interesting TEM image. The bigger sized spherical particle is silica nanoparticle. So on the silica nanoparticle, gold and silver bimetallic particle have been deposited. So the spherical particles are alloy gold silver nanoparticles. The single particle having both gold and silver atoms, and they are typically spherical shape. And if we do HR term, high resolution transmission electron microscopic analysis, so with 2 nanometer scale bar, see we can obtain the lattice fringes. So these are the Kapuchi lines. Dark and lighter parallel lines are called Kapuchi bands or Kapuchi lines. So if we calculate the distance between the two lines, that will give you the d-spacing value of the material. That d-spacing value will be converted into HKL value, and HKL value will be matched with the material present in the sample through the software. So that will give you the idea what kind of crystalline facets are available at the surface of the material. So this one is EDX, energy dispersive X-ray analysis. As I have told you already, the EDX will give you the idea about the presence of different elements in the sample. So my sample containing silica, which contains silicon and oxygen, silica, and gold, silver elements, and this copper peaks indicates the specimen is copper grid, and we can in a particular spherical particle we can see dark and lighter spots on the surface. So dark side, so you can understand the dark color indicates the presence of gold and the light color indicates the presence of silver, because silver having lesser atomic number than the element gold. So these are the selected area electron diffraction of the silver nanoparticle. So all crystalline peaks, the spherical, the circle patterns indicates the circle patterns with dotted lines indicates the crystalline nature of the sample, and these circles are correlated to the crystalline facets of different crystalline facets of silver nanoparticle. So these many information we can get it from the transmission electron microscopy, the presence of nano-sized particle, the structure of the particle, morphology of the particle, size and shape of the particle, and the alloy nature of the particle through light and dark regions, and the presence of different elements, and whether it is attached on the surface or it is separated from the support material. That kind of information we can see, and the crystallization of the sample also can be analyzed through the transmission electron microscopy. Thank you for the attention.